Hello friends, let's continue with another problem on PCM-TDM. In an earlier problem, we saw that the signals to be time division multiplexed were all band limited to the same maximum frequency, and therefore the Nyquist rate for them was same. In this problem, however, we will look at designing a TDM system in which not all signals are band limited to the same frequency. However, their frequencies are harmonically related, and therefore it will be possible to intelligently design a scheme in which all signals will be sampled at their Nyquist rates. So let us look at the problem. A signal is band limited to 3.6 kilohertz, and three other signals, namely M2T, M3T, and M4T, are band limited to 1.2 kilohertz each. These signals are to be transmitted by means of time division multiplexing. Set up a scheme for accomplishing this multiplexing requirement with each signal sampled at its Nyquist rate. What must be the speed of the commutator in samples per second? If the commutator output is quantized with 1024 levels and the result is binary coded, what is the output bit rate? And finally, determine the minimum transmission bandwidth of the channel. So, what is given in the problem are four signals, say M1T, which is band limited to 3.6 kilohertz, and M2T, M3T, and M4T all are band limited to 1.2 kilohertz. All are required to be sampled at their Nyquist rate. So what will be their Nyquist rate? That is the first part of the problem in which we are required to set up a scheme. So let us first look at the four message signals. Their bandwidths are 3.6 kilohertz, 1.2 kilohertz for M2, M3, and M4. The Nyquist rate is double the maximum frequency, and therefore for M1T the Nyquist rate is 7.2 kilosamples per second, that is 7,200 samples per second. Similarly for M2, M3, and M4T, it is 2,400 samples per second each. Now note that though the sampling requirement for all signals is not same, for M1T it is 3 times higher than that of M2 or M3 or M4T. And because of this harmonic relation, what we can do here is that in one rotation of the commutator, we take one sample each of M2, M3, and M4T, but 3 samples of M1T. In that case, it will be possible to perfectly sample all signals at their Nyquist rate. So let us look at such a scheme. So this is the arrangement. This is a commutator taking samples in turn, first from M1T, then from M2T, then again from M1T, then from M3T, then again from M1T, and then M4T, and then again from M1T. So this way, you can see all the signals are sampled at the Nyquist rate. So the scheme is like this. First, a sample is taken from M1. Let's say this line with a cross denotes sample from M1. Then a sample from M2 is taken. Say this is a sample from M2. And then again a sample from M1 is taken. So another sample again comes from M1. Say this is the sample. Then a sample comes from M3. Let's say this is the sample from M3. This is the sample from M3. And then again a sample comes from M1. So let's say this is the sample that has come from M1. And then a sample from M4. Say this is the sample from M4. And then again in the next cycle, there is a sample from M1. So this cycle continues. So we observe that in one rotation of the commutator, we get 3 samples from M1. So this and this are the samples from M1. M1T's samples. This red is the sample from M2T. This blue one is sample from M3, and the green one is the sample from M4. And then again, the next rotation of the commutator start taking sample from M1 onwards. So this is the scheme. And this was the first part of the problem. So we have set up a scheme for accomplishing this task, this multiplexing requirement. Now, what must be the speed of the commutator in samples per second? So see, the commutator is taking 7,200 samples of M1, 2,400 samples of M2, 2,400 samples of M3, and 2,400 samples of M4 in 1 second. So in 1 second, in all, so let me just number it. So this was part A. Part B, the commutator speed in samples per second is equal to, so 7,200 samples of M1, 2,400 samples of M2, 2,400 samples of M3, and 2,400 samples of M4. So it sums to 14,400 samples per second. So this is the commutator speed in samples per second. Now part C, if the commutator output is quantized with L equal to 1024 levels and the result is binary coded, what is the output bitrate? It's a simple part. So L equal to 1024, which can be written as 2 to the power 10. That means the number of bits per quantization level n is equal to 10, and therefore the output bit rate is equal to n times fs, where fs is the number of samples per second, the commutator speed in samples per second. So one sample is represented by 10 bits. So for 14,400 samples, we need 10 times 14,400 equal to 144 into 10 to the power 3, or 144 kilobits per second. So this is the output bit rate. And finally, determine the minimum transmission bandwidth of the channel. So the transmission bandwidth of the channel is given by the minimum transmission bandwidth is equal to NFS by 2. We know that 1 hertz of channel bandwidth can support 2 independent pieces of information per second through it. So assuming 1 bit representing 1 independent piece of information, the channel bandwidth required is NFS by 2, output bit rate by 2, which is 144 into 10 to the power 3 by 2, which is 72 kilohertz. So this is the problem. I hope it is clear to you. Thank you.